Hi guys, welcome. Today is day 16. So we're looking at lessons 58 and 59. So nearing the end of this unit, we have lesson 60 and then we'll start reviewing for the test. So this one we're solving percent problems with equations. Okay, so percent of a whole number is a part. So we know that obviously 75% of something is going to be less than 100% of it. So all the parts added up, if we're talking about a whole, add up to 100%. 32 ounces. So if we're looking at example 1, 32 ounces is 25% of a gallon. How many ounces in a gallon? So 32 ounces is 25%. We could do that as a decimal or a fraction. Okay. If we're doing it as a fraction, we multiply by the reciprocal. 1/4 times g would be 4/1, or just 4 times both sides. And that would give us 32 times 4, which is 128. We used a decimal, same thing, but we're dividing by 0.25 to both sides. So 32 divided by 0.25 is 128 ounces. So we use what we know about a percent, and then we have to either convert it to a decimal or a fraction. We can't divide by 25 because that obviously would not be the correct answer. So we use percents a lot. We just have to know that we convert it. So if we're looking at example 2, someone bought a used car for $8,500. The sales tax was 7%. How much tax did Mr. Valeskis pay? So we want to figure out what is 7% of 8,500. 7% of 8,500. So we could do this either as a fraction. Since we're talking about money and it's going to be easy to convert this to a decimal, I'd call this 0.07 times 8,500. Then we just multiply that out. Is $595. So that's what he paid in taxes, a 7% tax rate. So again, just set up a problem just like we do with fraction or decimal. Anytime we see is or of, is equals, of is multiplication. It's just we're using percents. So we got to think back to what we know about converting percents to either decimals or fractions. Sometimes it's easier as a fraction, sometimes it's easier as a decimal. All right, if we look at example 4, Blanca correctly answered 23 of 25 questions. What percent of questions did she answer correct? So now we're working with, we have a total. Let's use our own test. Our own tests are always out of 40. So let's say you got, let's say a 34 out of 40. That's the first question I always get is, well, what is this? What is this as a grade? What percent is this? Well, now we know how to calculate it. So let's go ahead and do 34 divided by 40, which is 0.85. So that's our decimal. We want to know percent. We know, what percent we got on the test tells us what grade we got. So we would multiply this by 100, or again, that's just going to be moving the decimal 2 places to the right. So 34 out of 40 is an 85%. And so you got a 29 out of 40. Well, what is that? That's how many I got right. That's the total number of questions we had on the test. 29 divided by 40 is 0.725. Multiply by 100 or move it 2 places. You got a 72.5%. So again, there's a quick way. If you get a test back, the number you got correct out of 40, do the division and then multiply by 100 or just move the decimal 2 places to the right. And that'll tell you what percentage you got. We'll go over those practice set problems together. Lesson 59, we're looking at experimental probability. So we've already talked about theoretical probability. You flip a coin, it can theoretically be heads or tails. Flip 2, heads or tails. Flip 3, heads or tails. Roll a dice, it can be 1, 2, 3, 4, 5, 6. Roll it again, it can be 1, 2, 3, 4, 5, 6. So we can calculate theoretical probabilities pretty easily. Well, heads, tails, it should be 50-50, a 1 in 2 chance every single time. But in experimental probability, that's how it actually plays out when we do it for, 10 tries or 20 tries or 100 or whatever it is. The longer you do the experimental probability, the closer it's going to get to that theoretical probability, but it's probably never going to be exactly the same. So if we flip a coin 100 times, theoretically it's going to be heads 50 times and tails 50 times. But experimentally, it could have been 61 times head and 39 times tails. Okay? It didn't work out to be 50 and 50 or 1 and 2, okay? Because obviously it's not always going to be the exact same. Now, if we carry that out over 1,000 or 1,000,000 flips, the more times we do it, it's going to get closer to that 50% or that 1 in 2 chance. But that's the difference between theoretical and experimental probability, okay, as they show right here. So experimental probability, the number of times an event occurs over the number of trials. So experimental probability obviously works out to be different than the theoretical probability. More than likely, there could be that chance we flip it 100 times and it ends up being 50-50, but it's probably going to be, around that 50%, but not exact because it's experimental. It's actually being performed. So a softball player hit 21 hits in 60 at-bats. Express the probability the player will get a hit in her next at-bats as a decimal number with 3 decimal places. So 21 out of 60, 21 was the number of times a hit occurred out of 60 at-bats. So that as a decimal number is 0.35. So then take it out to 3 decimal places, we would call it. So as a percent, we could say there's a 35% chance that she'll get a hit on her next at bat, or if you ever watch baseball or anything, that's why they say so-and-so is batting 300 or 280 or whatever. It's 0.280 or 0.350. So they'd be batting 350, which in baseball or softball is actually really good, even though it's not even half the time as, if you can hit a third of the time or ever hit that 400 mark, 0.400, that's really good. So we can use that experimental probability to come up with the likelihood. Now, that doesn't mean that over the next 100 times she's going to automatically get 35 hits. She could get 20 hits. She could get 50 hits. It just depends. But this is the experimental probability off of the actual events that have occurred. Experimental probabilities are used in sports, but business, weather, insurance, banking, a lot of things because we want to actually see how the numbers play out to give us an idea of should we invest, should we buy, should we save, whatever. Theoretical probability is used in games of chance, rolling a dice, flipping a coin, spinning a spinner, whatever it is. So let's look at this. The commuter plane flight arrives on schedule 2/3 of the time. So we can use simulations, the theoretical, to try and predict the experimental. Obviously, it's going to be close, but we can use simulations and theoretical probabilities to try and predict how events are actually going to play out. So the commuter plane flight arrives on schedule 2/3 of the time on any given weekday. Heather wonders what probability is that it will arrive scheduled on Tuesday, Wednesday, and Thursday in the same week. How could the experimental probability be found? Why is it impractical? How could the spinner at the right be used to simulate the experiment? So Heather could check the actual flight arrival times on Tuesday, Wednesday, Thursday for several weeks. The experimental probability is the number divided of times the flight arrives on schedule on all 3 days in a row divided by the total number of selected 3-day periods. This would take a very long time to conduct. So if we want to predict something, but it's going to take days or weeks or months or years to actually see how it plays out, we'd maybe want to simulate and use theoretical probability to predict what's going to happen instead of experimental probability. I've heard this when teams are playing in the Super Bowl. They have their supercomputers that they have run simulations of the game, and in their simulation out of 100 games, this team won 70 out of the 100 times or whatever. Obviously, that has no bearing on what's actually going to happen in the game, but it can kind of help people, predict what's going to happen more accurately. How could the spinner at the right be used to simulate the experiment on schedule, not on schedule? Well, we could spin this and say, okay, well, this is our flight pattern, okay, whether it's on time or not on time. And we have 2/3 on schedule, 1/3 not on schedule. So we can use this spinner to quickly, do 10, 50, whatever simulations to get, an experimental probability. Again, that doesn't determine what's going to actually happen, but it may be a quicker way to get some quick simulations to try and calculate, experimental probability. All right, practice set here we'll go over together. So that is all we have for today. We'll see you guys in class. Thanks.